What if I told you that a three-man garage operation, running out of a converted barn in rural Ohio, discovered something that McLaren, Ferrari, and Mercedes all missed? Not through million-dollar wind tunnels or supercomputers, but with a borrowed dynamometer, some welding equipment, and an approach so unconventional that professional race engineers literally laughed out loud when they saw it. This is the story of how conventional wisdom in racing got turned completely on its head by people who simply couldn't afford to think conventionally. And look, before we get into this, I want to be upfront with you. What you're about to hear isn't just a feel-good underdog story. It's a masterclass in engineering philosophy that has fundamentally changed how suspension dynamics are understood at the highest levels of motorsport. So buckle in, because this one goes deep. This is Motorsport Heritage, and I spend way too much time thinking about the moments in racing history where someone threw the rulebook out the window and went faster for it. If you're someone who loves the engineering side of motorsport, the genius hidden underneath the bodywork, the ideas that changed racing forever, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Picture this. It's March 2019 at Sebring International Raceway. The who's who of endurance racing are there. Factory teams with semi-trucks full of spare parts. Armies of engineers staring at telemetry screens. Drivers who've won Le Mans. And then there's Midwest Motorsports Dynamics, rolling up in a converted RV, towing a trailer they bought used off Craigslist. Their entire race budget for the season was less than what Porsche spent on catering that weekend. The paddock talk started immediately. Veterans pointed and snickered at their setup. The car, a modified Ligier JSP 320 they'd bought as a write-off from a crash, looked wrong to trained eyes. The rake angle was all off. The spring rates made no sense. The damper settings violated everything taught in vehicle dynamics textbooks. One senior engineer from a factory-backed outfit was overheard saying it looked like someone had set the car up using a smartphone app. And here's the thing. He wasn't entirely wrong. But what nobody in that paddock understood in that moment was that this wasn't ignorance on display. This was revolution. You see, Mark Dennis, Jim Catalano, and Terry Washington weren't stupid. They were broke. And being broke in motorsport forces you to think in ways that money never allows. Dennis had spent 15 years as a suspension technician at various IMSA teams before getting laid off when his team lost its primary sponsorship. Catalano was a mechanical engineer who had spent years designing agricultural equipment until the company relocated operations overseas. Washington ran a small machine shop that mostly produced parts for local manufacturing facilities. Together they had roughly $200,000 between them, a barn on the outskirts of Dayton, and an idea that virtually everyone in the professional paddock said was completely insane. Here's where it gets really interesting. In traditional racing setup philosophy, the kind taught at every performance driving school and used by every professional team at every level of motorsport, the approach is built on decades of accumulated, carefully validated wisdom. You start with spring rates calculated from corner weights and expected lateral G-forces. You set your ride height based on aerodynamic efficiency targets. You adjust dampers to control weight transfer rates between axles. Anti-roll bars are tuned to balance the car's behavior through corners. Toe and camber follow established curves derived from tire supplier data. It's systematic, it's proven, it genuinely works. But Dennis had noticed something troubling during his years working in the paddock. Every team was converging on essentially the same setups. Sure, there were minor variations, but everyone was working from the same fundamental playbook, the same simulation software packages, the same tire models, the same baseline assumptions about what actually makes a racing car fast. And here's the thing about that. When everyone thinks identically, everyone hits identical walls. The conventional approach assumes you're optimizing individual parameters toward theoretical ideals. Spring rates that produce the correct ride frequency for the expected inputs. Dampers that control oscillation within specific, well-understood bounds. Roll stiffness distributed to match the car's static weight distribution. Alignment geometry that maximizes tire contact patch area through the corner apex. It's all very logical, very scientific, and extraordinarily expensive to get precisely right at the level these factory teams were pursuing. Now, you might be thinking, well, if it works, why question it? And that's exactly the problem Dennis kept running into. Because what if the entire approach was answering the right question in the wrong way? What if the question itself needed changing? The birth of what would later be called the Dennis method started in late 2018, roughly 6 months after Mark lost his job. He was in his garage late one evening, staring at suspension data he had carefully copied onto thumb drives over the years of professional work. Nothing proprietary, just general setup sheets and telemetry exports from various cars he had personally worked on across different championships. Something in the numbers bothered him in a way he couldn't initially articulate. Cars with theoretically inferior setups would occasionally post genuinely competitive lap times. Not often. Maybe one race in 15, but enough to notice if you were looking. These outliers were always dismissed within teams as flukes. The driver having an unusually good day, track conditions that happened to suit that specific setup. Statistical noise in a complex dataset. But Dennis started plotting these outliers systematically, searching for patterns that everyone else had written off and ignored. And he found something that stopped him cold. The fast outlier setups had absolutely no consistency in their individual parameters. Spring rates were all over the map. Ride heights varied wildly from what aerodynamic models predicted. Damper settings appeared almost random when viewed through a traditional lens. But they shared one thing in common, something nobody in professional racing was measuring, because nobody had thought to measure it. The relationship between front and rear natural suspension frequencies under combined dynamic loading conditions. Not static conditions, dynamic ones. The kind that actually happen when a driver is simultaneously braking, turning, and managing a curb at 140 miles per hour. Let me explain this in plain terms, because this is where the whole theory lives. Every suspension system has a natural frequency, the rate at which it wants to oscillate when disturbed, like a tuning fork humming at its specific pitch. Traditional setup philosophy says you want front and rear frequencies within a certain range of each other, typically measured and validated under static or near-static conditions. But Dennis realized something profound. Under real-world driving conditions, braking, accelerating, and cornering simultaneously, these frequencies shift dramatically from their static values. And more critically, they interact with each other in ways that static measurement completely fails to predict. Think of it like noise-canceling headphones. They work by producing a sound wave that is precisely opposite in phase to the ambient noise around you, and the two waves cancel each other out. Dennis discovered through his data analysis that certain suspension configurations created a remarkably similar phenomenon. The front and rear suspension oscillations would interfere with each other destructively, canceling out specific, unwanted chassis motions. The car became incredibly stable and predictable, even though every individual measurement, viewed in isolation, looked completely wrong by conventional standards. The critical problem was that you couldn't calculate this effect using traditional methods. The interactions were too complex, too deeply dependent on real dynamic conditions that simulation software of the era simply didn't model, because nobody had known to look for this mechanism in the first place. The only reliable way to find these harmonic sweet spots was through exhaustive physical testing that would cost millions of dollars at a professional facility. Unless, of course, you got creative about how you tested. That's precisely where Jim Catalano entered the picture. Remember, he had spent years designing agricultural equipment, specifically combines and tractors that had to perform reliably on wildly varying, completely unpredictable terrain. The agriculture industry had developed suspension approaches that motorsport had never considered relevant, because racing happens on relatively smooth, controlled surfaces compared to a farm field, while agricultural machines have to function in genuine chaos. Catalano had worked on self-leveling systems that use predictive algorithms to adjust suspension behavior in real time based on terrain inputs. But more relevant to what they needed, he had developed low-cost methods for testing suspension performance using basic accelerometers and inexpensive data logging equipment that cost a few $100s rather than hundreds of thousands. Agricultural engineers had to be economical. Their customers were farmers working on tight margins, not Formula One teams with unlimited development budgets. That constraint had driven remarkable ingenuity in how they gathered and interpreted data. Together, Dennis and Catalano began developing their theory into something testable. But theory alone doesn't win races. They needed a car. They needed physical proof that this could work outside of a spreadsheet. That's when Washington became the third pillar of the operation. His machine shop was facing increasing pressure from overseas competition, and he was genuinely looking for something new to pour himself into. He had fabrication skills that the other two lacked, and more importantly, he had access to a dynamometer. A 20-year-old engine dynamometer he had purchased from a closing speed shop at auction. It wasn't sophisticated, but it existed, and it was theirs to use whenever they needed it. In October 2018, they pooled their available resources and purchased the wrecked Ligier. The previous owner, a gentleman driver who had put it into the wall hard at Road Atlanta during a GT Daytona weekend, practically gave it away to clear space in his trailer. The carbon tub was structurally sound, but everything else needed attention, which was perfect for 3 people with considerably more time available than money. Now here is where their approach diverged completely from anything the professional world would have recognized. Instead of trying to restore the car to correct factory specifications and then optimize from there, they deliberately used it as a testbed for their frequency interaction theory. Catalano designed what he called a harmonic resonance mapping process. Essentially, they would test thousands of different setup combinations systematically to identify the configurations where the destructive interference pattern emerged with enough clarity to be exploitable on a real racetrack. The testing process was genuinely extraordinary in its intensity. They would bolt on different spring rates, adjust ride heights by millimeter increments, change damper settings across their full range, and run the car on the dynamometer with Washington's shop floor covered in industrial rollers salvaged from a closed local factory. The car never physically moved from its position, but the suspension cycled through loads that approximated the forces of cornering, braking, and acceleration. Accelerometers were attached at every relevant pickup point, recording the response of the system to each input. In 3 months of 12-hour days, 7 days a week, they tested over 4,000 different configuration combinations. Their neighbors became convinced something deeply unusual was happening in that barn, hearing the engine running at all hours through the Ohio winter. But the patterns were starting to emerge from the noise in their data. Certain combinations of seemingly incorrect settings produced remarkably stable platform behavior. The car would receive an input that should have generated significant chassis upset, and the motion would simply disappear. The front and rear oscillations were canceling each other out exactly as Dennis's theory had predicted from his analysis of those historical outlier setups. The harmonic sweet spots were real. They weren't theoretical. They were physically measurable and reproducible. By February 2019, they had identified 12 setup configurations that showed genuine promise in the controlled test environment. But controlled testing only tells you so much about what happens at racing speeds on a real track with a real driver making real inputs. They needed track time, and private test days at professional facilities cost money they simply did not have available. So they entered the car in NASA endurance events, small regional competitions where entry fees were manageable, and they could run extended stints to gather meaningful data. Nobody paid much attention to them. They were just another privateer team making up the numbers at the back of a modest field. But the data coming off the car during those sessions was revealing something genuinely extraordinary. Their theoretical lap times, calculated using conventional methods from their spring rates and ride heights, should have placed them 3 to 4 seconds off the competitive pace. Instead, they were consistently within 1 second of teams with significantly larger budgets and more professionally prepared equipment. And here's the part that mattered most to Dennis specifically. Their lap times were metronomically consistent in a way that no other car in those fields was achieving. While competitors varied by 2 or 3 seconds between laps depending on fuel load changes, tire thermal state, and the natural variation of driving under pressure, the Midwest Motorsports car varied by half a second at most across an entire stint. Consistency doesn't generate exciting headlines. But in endurance racing, consistency is everything. A car that is 1 second per lap slower but maintains that pace without degradation for 4 consecutive hours will defeat a faster car that loses 2 seconds per lap as conditions evolve. Dennis's setup wasn't producing the quickest single lap in the data. It was producing the highest average lap speed across the entire stint duration. The destructive interference pattern was actively preventing the normal handling degradation that all racing cars experience as tires wear, fuel burns off, and brake temperatures cycle. This was the breakthrough they had been searching for in the data. So they made the decision to enter something that would actually matter. They submitted their entry for the IMSA Michelin Pilot Challenge race at Sebring, a genuine professional-level event. It was intended as their proof-of-concept moment. Show up, run consistently, gather richer data from a higher-quality competitive environment, and perhaps attract the attention of investors who could fund proper development of the concept. The scrutineers who inspected the car before the event were visibly confused. Everything was legal within the regulations, but nothing made sense to eyes trained on conventional setup wisdom. The front springs were 800 pounds per inch, considerably stiffer than any comparable car in the field. The rear ride height was 15 millimeters higher than aerodynamic efficiency models would suggest. The front anti-roll bar was completely disconnected. One technical official pulled Dennis aside quietly before practice and asked whether they needed any assistance with their setup. Dennis thanked him politely and said they were exactly where they wanted to be. Practice sessions made them an immediate talking point in the paddock for all the wrong reasons. Photographers were capturing images of the car in corners because it looked so visually unusual in motion. The nose carried too much height. The rear squatted dramatically under acceleration. The car rolled through direction changes in a way that looked almost like it was struggling. A data engineer from one of the Porsche factory programs pulled their telemetry up on the timing screens and used it in a briefing to his drivers as an illustration of what poor setup looked like in the data. He was not entirely wrong about what the individual traces showed. He was completely wrong about what they meant when taken together. The Midwest car was doing something that no individual measurement could capture. It was allowing specific frequencies of suspension motion to occur while simultaneously and completely canceling others. It appeared loose and unsettled to an observer's eye. In reality, the chassis was more controlled than anything else in that paddock. The visual language of performance that trained eyes had learned to read simply didn't apply to what this car was doing. Qualifying told the first part of the story. In a field of 38 cars, Midwest Motorsports qualified 15th, not a headline result, but for a 3-person operation running a rebuilt write-off against factory-supported entries. It was enough to draw genuine attention from the engineers who pay close attention to the timing sheets. The Porsche program engineer who had used their data as a negative example pulled their sector time breakdown after qualifying. In Sector 1, they were unremarkable. The high drag from their ride height cost them measurable top speed down the back straight. But in Sector 3, through the slow, bumpy technical section that Sebring is infamous for, their minimum corner speeds were inexplicably elevated. Through the carousel, one of the circuit's most demanding slow corners, they were carrying 4 miles per hour more than cars running twice their theoretical aerodynamic downforce level. Nobody in the paddock had an explanation for that number. Race day. 4 hours on one of the most physically brutal circuits in North American motorsport. Sebring is notorious for its surface transitions, concrete expansion joints, and bumps that expose any weakness in a setup with brutal efficiency. It is where carefully optimized configurations frequently come apart over the course of a long stint. The conventional wisdom for Sebring was to run relatively soft spring rates to absorb the punishment and accept some handling degradation as the unavoidable cost of surviving the distance. Dennis's team changed nothing from qualifying. Washington climbed in for the opening stint and settled into a rhythm within 2 laps. The times were 1 minute and 58.2 seconds, 1 minute and 58.5 seconds, 1 minute and 58.1 second. 1 minute and 58.3 seconds. Lap after lap, the same numbers kept appearing on the timing screens. Cars ahead of them were varying by 2, sometimes 3 seconds as they managed traffic, responded to fuel load changes, and began experiencing the early stages of tire degradation. The Midwest car just kept producing the same lap time, every single time, with a precision that timing engineers in the professional team's hospitality units began remarking on. An hour into the race, something measurable was happening in the gap between their 15th place position and the leading cars. It wasn't growing. It was shrinking. Not because they were getting faster in any absolute sense, but because the competition was getting progressively slower in the way that all racing cars do as conditions evolve through a stint. Tire degradation, brake temperature cycling, the natural behavior of suspension components under sustained heavy use, all the normal forces that pull lap times apart over a long race simply weren't acting on the Midwest car the way they acted on everything else in the field. The first pit stop cycle cost them positions they couldn't recover immediately. 2 minutes and 15 seconds for tire changes and driver swap versus the sub-60-second stops the professional teams executed with practice crews. Catalano took over and the lap times did not change. New driver, warmer track, harder worked engine, and the car was still posting 1:58. The BMW directly ahead had fresh tires, a professional driver, and a factory setup. It was marginally quicker in the first 5 laps after the stop, but as those tires moved off their initial peak performance window, the BMW's time started falling while Catalano held his pace without variation. By the 2-hour mark, they were running 12th. A Porsche developed a brake issue. A McLaren spun trying to recover lost ground in turn 17. And Aston Martin suffered a suspension failure, specifically a damper that had been overwhelmed by the cumulative abuse of Sebring's surface. The Midwest car kept going. No drama, no mechanical complaint, just relentless consistency in a race that was consuming everything around them. The turning point arrived at the 3-hour mark. A full-course caution for a Mercedes that had found the wall in the infield section compressed the entire field. Everyone pitted under yellow. Fresh tires went on across the field. Fuel went in. Drivers were swapped in team after team. Setup adjustments were made. Tire pressures tweaked. Anti-roll bar settings adjusted to account for the changing track conditions as the Florida sun worked on the tarmac. Teams were actively chasing the circuit's evolution with the tools available to them during a pit stop. Midwest Motorsports changed absolutely nothing. They couldn't. Their setup only produced the harmonic cancellation effect at precisely the configuration they had identified through thousands of hours of testing in Washington's barn. Any adjustment, however small and well-intentioned, would disrupt the specific frequency relationship between front and rear that made everything work. Washington climbed in for the final stint with the car in exactly the same state it had started the race. What followed over the next 40 minutes was something that nobody in that paddock had expected to witness. The track surface was fundamentally different from the morning. Rubbered in, hotter, with the concrete expansion joints having moved as the temperature climbed through the afternoon. Cars that had been genuinely quick in the earlier stints were fighting their setups, engineers on pit walls frantically adjusting tire pressure targets and talking drivers through balance changes lap by lap. Washington's times were 1:58 still. Teams that had been 2 full seconds per lap faster in qualifying were now lapping at his pace or slower. The setup that had looked disastrously wrong to every trained eye in the paddock that morning was producing its fastest relative performance at the precise moment when everything that had been fast was fading. With 40 minutes remaining, they were running 8th. With 20 minutes left, a tire failure took out the 5th-place Audi. An electrical fault ended the 7th-place McLaren's afternoon. Suddenly, Midwest Motorsports was 6th with a converted barn build, a 3-person crew, and a setup that professional engineers had publicly mocked less than 12 hours earlier. Engineers in the professional team garages were scrambling. Telemetry was being pulled and analyzed in real time. The damper histograms from the Midwest car showed suspension travel ranges that should, by every conventional model, have resulted in bottoming out and catastrophic handling instability. But the lateral G-traces showed cornering behavior that was smoother and more consistent than anything else still running in the field. The data was internally contradictory in a way that no existing model could explain. because the model that explained it hadn't existed until 3 people in Ohio invented it. 15 minutes to the flag. A charging Porsche, pushing hard for a podium finish, caught them through the infield. Washington didn't fight it through the braking zone, but through the carousel, that same corner where the Midwest car had been inexplicably fast in every practice session. Washington got a better exit. The setup that allowed more controlled power application earlier in the corner exit gave him a run down the following straight, side by side into turn 10. The Porsche took the conventional optimal line. Washington ran a wider entry, carrying more speed because the setup stability let him, using a line that physically wouldn't have worked in any other car in the field given the bumps on that particular approach. On the exit, he was ahead. 5 laps remaining, the 2 cars traded positions through different track sections. The Porsche stronger in Sector 1. The Midwest car systematically faster in Sector 3 every single lap. The television commentators had finally found them in the broadcast, though they got the team name wrong initially. The David and Goliath story was writing itself in real time on the timing screens. Here's what most people don't realize about what Washington was doing in those final laps. He wasn't racing the Porsche in the way that professional drivers race each other. He was simply driving his laps. The same 1:58s he had been posting since the moment he left pit lane. The setup Dennis had designed was so consistent and so predictable that Washington could place the car at exactly the position he needed it, at exactly the speed he needed, lap after lap without variation. The Porsche driver was the one doing all the work, fighting degrading rear tires, managing an increasingly unbalanced car, making micro-adjustments through every corner that were costing fractional seconds that added up. The last lap began with Washington holding half a second. The Porsche made one final committed attempt through turn 7, but the Midwest car's corner exit was again measurably superior. Through the final complex of turns, where Sebring's surface is at its most punishing, the Ligier moved through with a fluency that a professional observer would have called almost serene. Across the timing line. 5th place. The paddock reaction was immediate and significant. Engineers from multiple factory programs were at their pit area before the cool-down lap was complete, asking questions, photographing the setup, trying to reverse engineer what they had just witnessed. Dennis was diplomatic in his responses. He spoke about holistic balance and dynamic optimization, without revealing the specific frequency interaction principle at the core of what they had built. Catalano, constitutionally unable to fully conceal his engineering excitement, dropped references to agricultural suspension theory that went completely over the heads of the motorsport specialists asking the questions. Washington said they got lucky and smiled. Nobody in the paddock believed him. That night, the computational resources of multiple factory programs were directed at understanding what had happened. CFD runs, suspension kinematic analyses, millions of dollars of engineering capability pointed at a converted barn operations setup sheet. None of it produced a satisfying explanation using the tools they had available, because the mechanism they were looking for wasn't in any of the models those tools were built on. The Porsche engineer who had used their data as a negative training example that morning sought Dennis out and publicly apologized, specifically acknowledging that he had allowed his assumptions to override his observation of the actual evidence. It was a genuinely gracious moment in a paddock that doesn't always produce them. Within a week of that result, Dennis received contact from 3 major programs offering consulting arrangements. Catalano was approached by a suspension component manufacturer interested in commercializing their testing methodology. Washington received inquiries about custom fabrication work from teams wanting to explore similar concepts. They declined every offer. Instead, they chose to publish their complete findings openly, not in an engineering journal behind a paywall, not in a racing publication with limited circulation, but on a freely accessible website with full data, complete methodology documentation, and the theoretical framework behind frequency interaction, suspension tuning. They made it available to anyone who wanted it. Dennis explained the decision simply. Racing had become too expensive and too exclusive. The same programs with the largest budgets consistently won because they could optimize traditional approaches to a degree of precision that smaller operations couldn't match. The publication of the Dennis-Catalano methodology was a deliberate attempt to provide a different path, one where rigorous thinking and careful testing could substitute for computational resources and budget scale. The impact on the broader community was immediate and genuinely divisive. Established suspension manufacturers disputed the theoretical basis. Several prominent race engineers published detailed technical rebuttals, but privateer teams and smaller professional operations around the world began experimenting with the principles, and the results that came back were consistent enough that the professional establishment couldn't dismiss them indefinitely. Within 6 months, variations of the approach were being applied across multiple categories from karting to GT racing at national level. The major factory programs eventually adapted, because they had to. Mercedes developed a computational model capable of predicting frequency interactions, though it required supercomputing resources to run in anything close to real time. Ferrari developed active suspension systems capable of adjusting harmonic relationships dynamically during a lap. Red Bull brought Catalano in as an external consultant, a relationship he insisted on maintaining remotely from his barn in Ohio throughout its duration. But the technical innovation, significant as it was, wasn't the deeper impact of the Midwest Motorsports story. The deeper impact was philosophical. It demonstrated that racing's accumulated conventional wisdom could contain fundamental blind spots. That approaching a complex problem from a completely different disciplinary background, in this case, agricultural engineering, could reveal mechanisms that decades of specialized motorsport engineering had missed entirely. It briefly democratized speed in a way that the sport hadn't seen since Colin Chapman was building Lotuses in a garage and rewriting the rulebook on what a racing car needed to be. Midwest Motorsports raced 3 more times after Sebring. They won once, at Mid-Ohio in wet conditions, where the setup stability advantage was amplified by a surface that punished every car in the field except theirs. But the attention that their results generated began changing the nature of the project in ways the 3 of them hadn't anticipated or wanted. Sponsors appeared with requirements. Investors arrived with expectations. The straightforward pleasure of 3 people solving genuinely hard problems in a barn was being displaced by business conversations and contractual obligations. So they stopped. They sold the car to a museum and returned to their lives. Dennis works as an independent suspension consultant. He works exclusively with underfunded teams. Catalano returned to engineering, applying racing-derived principles to suspension systems for emergency response vehicles. Washington's machine shop now derives roughly half its revenue from racing team fabrication work. The Ligier They campaign sits in the International Motor Racing Research Center at Watkins Glen. There is a specification plaque beside it listing the numbers that still produce visible discomfort in conventionally trained engineers who read them. Front springs 800 pounds per inch. Rear ride height 80 millimeters. Front anti-roll bar disconnected. And there is a second plaque containing a quote from Dennis that matters more than any of the setup numbers. We didn't prove that conventional wisdom was wrong. We proved that unconventional wisdom could be right. In racing, as in most things, the biggest barrier to genuine innovation isn't technology or money. It's the assumption that the way things have always been done is the way they must always be done. The frequency interaction principle is now formally taught in engineering programs. It appears in textbooks under the name Dennis-Catalano Effect. Major racing series have had to revisit setup regulation windows because the previously reasonable boundaries now arbitrarily exclude configurations that the evidence suggests could be legitimately faster. The Midwest Motorsports story isn't ultimately about suspension frequencies or harmonic cancellation physics. It's about what becomes possible when people who cannot afford conventional thinking are forced to think differently. It's about the particular danger of expertise solidifying into dogma. It's about the enormous cost of the assumption that because something has always been done a certain way, it must be done that way. Racing had spent decades converging on optimal solutions within a framework nobody questioned. What it needed was someone to question the framework. That turned out to require people who couldn't afford to accept it. The next time you watch a race and notice a car that looks wrong, carrying too much height, moving in ways that trained eyes say shouldn't be fast, look again. It might just be someone who found a better question to ask. Because if 3 people in a barn in Ohio can unsettle the assumptions of programs spending hundreds of millions of dollars per season, the question isn't whether that kind of breakthrough can happen again. The question is where it's happening right now that nobody has noticed yet.